So good afternoon, everybody, and welcome to this igus webinar. This one is about robot cable management, and the title that we have today is using e-chains instead of corrugated tubing. If you have used robots or you are maintaining robots in a factory or you're purchasing them, you'll be aware of the different types of cable management that can be used. And this webinar is designed to help you understand better the different options and to go in a little bit more deeper as to what the differences are and how those differences might be employed to benefit your processes and operations. My name's Justin Leonard. I'm one of the directors at igus. We're based in Northampton, and we supply what we call plastics for longer life, so any kind of plastics that help with movement, so from bearings to cable management systems. And this is our background to the webinar today. At any time, you feel free to use the Ask a Question function within the webinar. And what we will do is gather up the questions at the end and go through them, and hopefully be able to answer all of your questions at the end. So please do ask those at any point, and we'll try and get to them. So let's start. Let's look at a bit of background to robots and their increasing prevalence in industry and automation. So here's some background figures, interesting ones. These are fairly well known figures. So robot sales last year were getting towards 300,000, 290,000 odd, but they're predicted to rise to over 500,000 by 2020 and 800,000 by 2025. And that's a pretty fast rise. The other interesting area of robotics, which is set to grow very, very quickly, is collaborative robots. So robots that can work side by side with humans safely. And they're set to grow from almost nothing in the last few years to 400,000 by 2025. And to put that in context of a market value of robots is going to double between 2016 and 2025, which is a pretty big growth. So what we can see is that robots are becoming increasingly popular and increasingly numerous. So here, if you just Google robots, you'll see all sorts of images will come up showing you all sorts of different places where they're used. So the most common one here we see is automotive manufacture, one of the very early adopters of robotics into production processes. But we can see plenty of other areas where these are used. So these are smaller universal robots in smaller operations. This robot here, although it's painted matte black, a bit harder to see, but this is in visual effects for movies. This one here even is a robot ride, which is where people can sit in a seat held on the end of it and get spun around, which is, again, a very novel, interesting use far away from manufacturing. But all of these uses are becoming increasingly common, and plenty of other operations as well that you don't see every day. So with respect to cable management, what is the current state of the art for carrying cables and services to the end of the robot, whatever the function happens to be? And at the moment, the state of the art is corrugated tubing. In whatever form it is, in whatever size or shape or manufacturer, it is corrugated tubing with accessories such as brackets, as you can see here, and sometimes spring retraction systems and other kinds of accessories that go with that. And that has served the robot using community very well for a long time. But what we're starting to see is an increase in problems occurring with that type of cable management system. And we're going to talk about for a moment now about why that is and why that's increasing. So here's some images that you can see that just show some of the some damaged of these corrugated tubes, damaged versions of these. So some split and taped up, other ones where the springs are within the hose has been torn out, so that again the tube is ruptured. Some here where the tube has just gone, it's broken off completely and left the cables exposed. But why we're seeing this increasingly, but why does this happen? Well, it happens because of one of the benefits of the corrugated tube and one of the reasons why it was used, which is that stretch within this is allowed. The stretch in the hose is what allows it to cover lots of complex movements. The problem with that is that any strain and twist that occurs at the robot because of the robot motion gets directly placed onto the cables and hoses. So the hose itself, the corrugated hose, stretches and twists, but the cables and hoses don't. In fact, they get a lot of strain put on them, and well, they could strain and twist. Strain and twist, and that leads to breakages within them and intermittent faults and problems with the cables and hoses themselves that are inside. One of the other downsides is that twist is not allowed. So twist is very, very limited in a corrugated tube. As soon as you start to twist it, this is where you'll see some of these issues that you see here with the tube rupturing. And that's because it doesn't have a freely twisting sort of structure. And that's what forces the tube to split. So the problems that we're seeing increasingly and that customers are bringing to us are that the cables and hoses are getting damaged because the system is stretching but damaging the cables and hoses underneath, but also that the hose itself is breaking. And that's the most common sign that you'll see is telltale signs of rupture and splitting of the hose. So I want to just explain now where we're focusing on within the robot motion today, because there's lots of, there's up to 7 axes on a robot, as shown here, but actually most of them are fairly benign. So if we look at axis 1, you can have a rotating chain system around the base. 2 to 3 is usually very benign, very little movement from here. Where nearly all of the motion occurs is between axis 3 and 6. And nearly all of the rotation on a robot happens at axis 6. But if you combine 5 and 4 and you're spanning from 3 forwards, then that area has a lot of twist and a lot of motion. Axis 7, of course, is the axis that supports the robot's movement itself, and again, relatively benign. So axis 6 is what we're focusing on today, and this is the area where corrugated tubes being used have their limitations, and where the use of a true energy chain can offer something a little bit different. I guess another question is, why is this happening so much more now than before? And I think our experience is showing that the reason it's happening more and becoming more of an issue is because early adopters of robots maybe haven't used the full motion capability of a robot. And in fact, manufacturing processes are using the full capability of a robot much more now. And so the rotations at all of the axes, but particularly at 4, 5 and 6, are becoming much more utilized to allow some much more complex operations. And also robot cells are often more compact and more tightly fitted in than before. And again, this leads to some tricky requirements on the programming, and the robots again have to move in a much tighter space. And I believe that is why the current state-of-the-art of corrugated tubing has had its issues with with splitting and twisting because of the tighter motions it's being put through. So when I mention a true energy chain as opposed to a corrugated tube, what do I mean? Well, an energy chain, often people think of it as cap tracking or drag chains, but it can also be in a round form, and this is what you see here. And what a true energy chain is something that is a link-by-link construction where the links snap together. And so you can see 3 key features here of a round energy chain. So first of all, each link has a defined minimum stop radius stop. So as the links bend, you can see in the photograph here, they hit the square stop on the edge, and it means that there is a natural minimum bend radius. That means the cables don't get bent tighter than they can cope with. The second feature is the ball and socket that we see here, which is what we join the energy chain together with through the middle. And it's very, very easy to lengthen and shorten, simply snapping more links on or taking them off. But also it has a very strong tension strength through the middle of this. So it can take a very high level of tension, and that tension, therefore, is not being put directly onto the cables. So the chain here, the energy chain, doesn't stretch like a corrugated tube would. It stays at exactly the same length, and that prevents damage to the cables and hoses. The final part of the energy chain feature is the torsion stop. So as you turn in a torsional way this system, it will stop at our system stops at around about 10 degrees per link. And that means, as you can see here, there's a very soft twist is allowed, and you cannot over twist a cable or hose. This is particularly important with hoses, things like air hoses, pneumatic hoses, or fluid lines of any kind, where if you were to twist them too much, which can happen with a corrugated tube, that the hose is free to move inside there and to twist as much as it can. But the problem is that would restrict fluid flow. And there are certain operations, things like blown rivets and screws, where screws and rivets are blown down a tube, but that can become very, very critical and very problematic if there's not a twist stop, a torsion stop built into the system like we do with a round energy chain like this. So with the types of energy chain that we offer, round systems that can be put onto a robot, we offer these 5 styles here as basic styles. So the first one is a fully closed system. So as you look through the structure, you see the ball and socket joint, and then the outer structure is completely closed. Now that gives maximum protection for operations like welding or anywhere where there's a lot of dirt and debris, but of course it means you have to feed the cables and hoses through the chain system and then potentially terminate them afterwards. We then have an easy style, which is what you see on this side, which has a split along it, which means you can press fit cables in afterwards, but in every other way it's still very protected. It's very closed, and all but the smallest particles shouldn't get in, but it means you can swap cables in or out, including ones with large connectors on, very quickly. Incidentally, because of that split, you could in theory have a reduction of strength in the torsional sense with this chain. So what we do here is what we call our B version, is we put a cap on the ball here which stops the system getting twisted out, because that split has allowed more flexibility. So it's still very, very hard to accidentally unclip that ball and socket joint just through the normal operation of the robot. We then have 3 other styles of round energy chains, true energy chains. There's the Triflex R Light, which is very open. It doesn't have this fully closed outer, very, very open, just for very light duty cable management. And then we have 2 versions that actually pop open. Rather than pressing cables in, you can see through the section here, they either have a crossbar with a very open system or a fully closed lid, which can be opened by handle with a screwdriver and allow cables and hoses to be put in from the outside quickly and then snap shut. And that offers a slightly different set of benefits to the easy style or closed styles. Once you have a true energy chain which doesn't stretch and has a limit on the twist, that immediately limits where it can follow the robot's head at axis 6. And so you then almost certainly have to start considering retraction units. And a retraction unit, as you can see on this robot here, is something which simply allows some extra chain to be paid out as axis 6 rotates and twists. And that means that when it untwists and goes straight, the chain gets pulled back onto the robot rather than hanging down in a loop and getting in the way of the workpiece. And in more and more complex operations and small robot cells, that can become an issue. And because it doesn't have any natural twist in it, the chain generally will need some sort of retraction unit in most cases to ensure that it retracts properly and smoothly. And that is one of the features that allows the chain to operate without stretching. So we have 3 styles here, very small ones. We have a roller that keeps the chain pushed back, and the power for that is through an elastic bungee. So this is a very small, simple, light system. Then the mid-range of systems, which is the same as the photograph on the robot you can see here, has fiber rods, and you can probably just see the shape here. The fiber rods that are inside here, these are glass fiber rods, finish about here, and they offer a natural flexural retraction force to pull the chain back in this direction. Finally, when we look at very heavy-duty welding robots that might have very heavy water hoses or copper hoses with a very large fill weight that would be very difficult to retract just using fiber rods or elastic, we then move on to our RSP system, we call this, which is a pneumatic retraction system. So here we have a cylinder, there's a small reservoir underneath, and basically you tune the amount of air in the system to give a retraction force which is correct for the robot filling. Very simple to do, and then it stays at the same tension as you set it up on the beginning, and will keep retracting at that force. And that means if you add or take away filling, you can easily tune it to match that exactly. One new area which has been causing some new designs to be formed is laser welding operations which have these very large laser-like cables, and they are particularly fragile, and you have to be very, very careful with the bend radius that they go through. So with the previous systems, going back to this slide, you can see that there's a very tight bend radius on our retraction system to keep it compact. That would not be appropriate for some operations, particularly laser-like cables, where they need a very large minimum bend radius. So what we've developed here is a linear retraction system, which the retraction length, the part that can be pulled back, is between these two brackets. And again, this is a very heavy elastic sort of powered carriage here, but then the curve that's needed to allow this to follow the contours of the robot is allowed to be a much larger loop, and this is quite sympathetic to the laser light cable. So I'm just going to run a little video now that shows you how each of these systems operates and what they look like. In operation. It's an animation. So you can see here, this is the plate that the system runs on, and as we move into a plan view over the top of the robot, you can see that that is the retraction area. So there's a length of chain which is restricted by one of the donuts, one of these round rings here, and that is the retraction that keeps the energy chain out of the working area. And you can see the two orange fiber rods inside there. And once we go to a pneumatic system, it simply sits on a carriage. You can see the pneumatic line in here, and the cylinder is underneath. And that simply retracts exactly the same way, but offering a much higher force. Again, all of these systems, even the pneumatic one, are very compact. They lay very flat and flush to the top of the robot, so they don't take up too much more space. And then the little baby of the family, I mentioned this little bungee powered system. So you can see on a very small carriage, very low profile, and I believe this weighs around about 1.8 kilos. So this is a very important addition for smaller robots, desktop robots, or larger robots that have a very, very small number of services that you're trying to get to Axis 6. Here we see the linear system, and again you can see that's on a bungee pulley system. Quite a number of bungees offers a very large retraction force, and again this keeps it running in parallel above the robot arm, so very compact, and it keeps everything nice and linear. And then the arc, the curve that forms behind that, is then a very large radius and allows the cable to behave as you would wish it to without getting damaged. So a true energy chain can be used with the retraction system. However, there are some special applications where it's called upon to have cables and services, cables and hoses to be mounted directly from a robot cell, either above or from one side of the cell, basically not necessarily on top of the robot. And we have a couple of solutions that we've developed to allow for this, which is a fiber rod module. First of all, this is the one on the top left here, which again has the same fiber rods in, and the whole system is gripped at the back. That mounting bracket, of course, here is on a robot, but it could be on the robot cell as well. And the other option is a flex bar, a very flat bar, a reinforced plastic retractive bar, which supports the chain through a cable. And again, this one is shown on the robot, but this could just as well be off the robot somewhere. And this allows operations where you need to go directly from something like a fluid dispenser and not go via the robot, but just jump straight to Axis 6. The other thing that we're seeing these kind of applications be used for is when a robot has to work with 2 or 3 different types of head that have their own services attached, so gluing head, handling, welding, and each head that the robot picks up and uses has its own pack of cables and hoses that it needs, and that could be picked up and put down, and each one of those could have a retraction system. That wouldn't work very well on the robot, but it could work really well off the robot. And so again, a true energy chain, because of the lack of twist or stretch in there, does need to have some sort of system like this accounted for. In fact, corrugated tubes often don't have enough flex either and still need some kind of spring balance or retraction system above them on systems that run from a cell straight onto a robot head. And of course, as with corrugated tubes, there are a lot of accessories that you will need to ensure that an e-chain works really well and for a very long time on a robot. Even though it's a different technology, it still requires, for example, covers to stop paint or glue or welding spatter to get on them. These kind of donut rings to protect the chain if it's whipping around and moving very, very fast or could potentially get caught in sharp angles. Adapter plates to allow you to fit extra valve blocks. So if the valve block would normally be where the retraction system is, you can put it on the side or above or below the chain. And of course, tennis rackets or lollipops, whatever name you use for them, and the end brackets that hold the system on, complete with strain relief to hold the cables in place and stop them migrating through the system. So again, we offer a full suite of these, but that's something that you will need to look at if you're using an energy chain instead of a corrugated tube. Here's 4 examples, configurations that use slightly different energy chain technologies. So I'm going to start from the top left and work through these. So this system allows a post in the corner of the cell to bring the services up, and then they jump across from the back of axis 4 and then straight down to axis 6. Actually, there's no retraction system here, so this would be used on a robot with very minimal axis 6 and axis 5 movement, where retraction is not actually necessary, that there's enough flex in the normal system to allow for that. Then here we have a fiber rod module, so the system looks a bit like a fishing rod being held and bent down. That adds a little bit of retraction, a little bit more than the first system, and again then it runs from axis 2 back to off the robot to pick up the services. So this would be a slightly more complex system with a little bit more allowance for motion. Then the bottom left, you can see another system, and now we have a pneumatic retraction system on. So this one would allow a lot of motion on axis 5 or 4, 5 and 6, and with a lot of high strength pullback force. So this could be for something with a very high fill weight. And again, we take the services out of axis 3 and then out onto the cell wall. And finally, another system here which has a simple retraction system, but this runs all the way out round, and now we have an axis 1 energy chain system to cope with anything up to 540 degrees rotation at the base. So less movement at axis 4, 5 and 6, but quite a lot at the base there. So what you can see is that this, in a lot of ways, is a bit of a Meccano set that you can take different components of it and put them together to get a solution and get all the benefits of the energy chain. So reducing the damage on the hose, on the carrier, and on the cables and hoses themselves, but without having to have a high cost. You can have exactly the system that works for the motion that you need at precisely the right cost. So you don't have to have high levels of technology that cost you a lot of money in every application. One very crucial part that often gets overlooked is the cables themselves. Cables are often used with very high levels of twist, particularly around axis 6 of a robot, and often this leads to intermittent faults and problems arising from that on the tools themselves. And this is especially critical, we have found through our research and development on this, with screened cables. And that's because most screened cables have a woven shield, a braided shield. And when that is twisted, one side gets put under huge tension as it's twisted, and often the cores of the shield will snap. And that allows something that can puncture the outer jackets and start to cause shorting. So we've developed a whole family of cables. We call these CFROBOT, but are robot grade cables, and they have different layers of things like PTFE tape to allow the twist to be dissipated through the cable. But also the screen is a one-sided screen, so that as it rotates, it doesn't snap the shielding element wires and therefore cause shorting. And that's something you need to consider when you're putting together a robot package, to make sure that you have used the right cables that have a rating for twist. For example, here we show plus minus 180 over 1 meter, and that's guaranteed for 3 million cycles, for example. And that's the kind of thing you need to look at, and that could equally apply to fiber optic, as you see here, as well as power and data. The reason why that we know that we can guarantee that for 3 million cycles is because we take the testing of this very seriously. I won't run the whole of this video, but the start of this shows that we have 4 robot cells And this is how we do our testing. We test billions and billions of test cycles a year, including on our 4 robots that are running all the time and putting very severe torsion loads in. We also additionally run our energy chains. You can see the 3D energy chains here, the Triflex are round robot energy chains being twisted and manipulated there with cables inside, and we're constantly testing these kinds of operations to make sure that the chain itself and the cables can cope with the twist loads that will be put on it in a normal robot application. And of course we have lots of linear systems, which is what we are very well known for, but the round multi-axis robot systems, as you can see there, we take that testing just as seriously and have a huge amount of testing going on for that. Finally, I just wanted to share a few pitfalls that we have experienced over the years and just share 2 or 3 key points that might help when you're first considering a robot cell or fitting the cable and hose package into a robot cell, that we have learned along the way from years of doing these, and that is well worth you knowing, so that you can avoid the pitfalls that can arise from it. The first one is there's no such thing as a universal system. It's very easy to want to have a universal system that can be used on any robot application, and then you can reprogram it for a different operation and it will work fine. And many systems, particularly the retraction unit systems, are as close to universal as you can get. But our experiences don't, that often when something is reprogrammed, then there's a motion there which just behaves slightly differently as it interacts with the cable management system and the retraction unit. So however flexible you make it, it doesn't always mean it will be completely universal. So don't assume that. It might well work when you reprogram, but it's something that you need to consider, being very careful to run everything through the program, which leads on to my second point, that there's no substitute for careful testing and tuning. And that means you have to factor time in when you come to commission a robot cell with a new cable management system on it. Please put plenty of time in for testing and tuning. This means running the full program, probably at quarter speed and half speed, and looking for any areas where the cable management system could get caught or damaged, and then running at full speed and having a good test period for that, and accepting that that might require some tuning. And that also leads to the third point on here, that you might even need to do a small amount of reprogramming. The great news is that robots are much easier to reprogram or to tweak than they've ever been in the past. But again, it's something that is well worth allowing some time for, because when the robot system is running full speed on a new program, it might be that there's a motion that hasn't been considered on the design of the original dress pack, the original cable and hose package, and that could lead to problems. And it might be that you can program your way out of those problems very easily by changing the direction that the head approaches, or that the motion is done from. And very small changes can make a huge impact on the reliability of a complete system like this. So that was a very quick whistle-stop tour through our experiences of developing and using energy chains, true energy chains on robots rather than corrugated tubing. So just by way of summary, we know that our customers are getting huge reliability benefits using true E-chains, so link-by-link construction, rather than using corrugated tubes, because of the benefits of not damaging the cables and hoses with the twisting and stretching, and not allowing the corrugated tube to get split, because the E-chain has a natural twisting motion built into it. However, when you're using these, you should consider very carefully whether you need a retraction system. It may be that you don't, but if there's quite a large amount of motion at axis 5 and 6, then it should definitely be considered. And there should be many types out there for you. We certainly have quite a number, and that will allow you to choose something which will be appropriate for what you need cost-wise and strength-wise. The third summary point is that cables should be torsion rated. Again, please don't overlook this. This is something that causes no end of problems, that we chase around potential issues all over a robot and find that it's something as simple as the cable, and usually around axis 6, where a cable is that's on a tool of some kind is being over twisted, and the screen is breaking down and causing problems with intermittent faults. So look for a torsion rated cable, particularly from the axis 3 to 6 parts of your robot. And finally, in your program management, when you're looking at replacing or first fitting robot systems, please allow time and the availability of programmers to allow some testing and also tuning once the system is installed. Don't assume it will be a universal system. That's very hard to achieve, but accept that it will take a little bit of time to tune and to program correctly, and just to avoid any pitfalls later on in the actual regular operation of the robot. Now, once all of these things have been considered and done, you should have a system which, as long as the robot is doing the same operation, will last for a very, very long time and work very, very reliably for you. When a robot gets reprogrammed to do a different operation, then consider these points again. And if you do that, then you should have no problems at all with using a true E-chain instead of a corrugated tube and getting the reliability benefits of that. So that concludes the presentation part of the webinar. Hopefully you've had a chance to think about some questions and to put them through to me. So if you'd like to, and if you haven't done that, then please do that now. There's an opportunity to do that. You can see on your screens there's a question button. Please do that now. I'll allow a moment or so just for the last questions to come in, and then we will start to go through them and answer them. Thank you very much. I'll allow a moment or so just for the last questions to come in, and then we will start to go through them and answer them. Okay, so I'm just looking through the questions now, and we're going to start straight away with a question from Keith, which is, how easy is it to lengthen and shorten the Triflex R system? Well, as I mentioned before, it's a ball and socket joint, so a couple of things to be really clear about is you don't need to have there's no wires or nuts and bolts or anything holding each link together. It's a polymer ball and socket that's molded into each link. It's a single piece construction. All that means is that that you need to do is to twist the links apart from each other. So on the smaller size Triflex Rs, that's relatively easy to do by hand. On the bigger ones, you need a little bit more leverage to twist them in a rotating movement, and you can do that. There's a little witness mark molded in the side to allow you to push a medium-sized flat blade screwdriver through, and that then rests on the ball, and then the screwdriver acts as a lever to allow you to get more twisting moment. On the split style ones, I talked about a B version with a little cap on the ball and socket, which because of the way that the split style, it has a little bit more flexibility. We don't want that to come unpegged accidentally, so we put a bit of extra retention force into that. And again, the simple way to do that is to put a tool. We can provide that tool, but it's essentially like a hex key, an Allen key, which you put underneath. You push in through the link underneath the ball and socket, and then just wiggle the link in a sort of shearing moment, and that will come apart. However, in a longitudinal force sense, then that will definitely not come apart by accident. It can take a very, very high force. So simply twisting them apart and then adding them on is even simply you just push the ball into the socket and it'll snap in, and it'll be in place. So nice and simple to do. Thank you very much for that, Keith. Second question I've had come in is from Antonio. In what situation should you use the flex bar? So this was something I showed. This is a rarely used part of our toolkit, but it's a part of the toolkit that exists. And the idea is of the flex bar is it's a retraction system which can be used where the Triflex R needs to be suspended in some way. So either the flex car can be attached to another part of the cell as well as on the robot if you need it, but it's where the Triflex R will be suspended underneath. There are some situations where you need a lot more flexibility of the chain system than a normal retraction system gives you, and suspending this from a flex bar can be one of them, along with the fiber rod modules as well. The flex bar will just allow a little bit more twist and a little bit more free motion because the Triflex R is suspended underneath it on a rope, on a cord. So thank you for that, Antonio. Another question that's come in from John. This is a really very important question. What if a cable fails inside your system? Right, so if a cable were to fail inside the Triflex R system, it would depend on getting that out, would depend on what style of system it is. But if it's an openable style or an easy style, then all you need to do is undo the brackets which hold the Triflex in, and they're simply held by finger catches. You open 2 or 3 of those and with a finger catch, and then the bracket will open, and then you lift the Triflex R out so you can get to it, and then either open the links that you need with a screwdriver or by hand if it's a TRF style, openable style, or pull the cable through the split if it's an easy style. If it's the closed style, which is, I think I said in the presentation, is really more for very heavy-duty welding applications or anywhere where you can't allow debris in, that's a little bit more tricky. And if the connector is small enough, you simply pull it through. It's a very smooth, sculpted system on the inside of the chain. But if it's bigger than that, you would need to undo the quickest and easiest connector and pull that through. So generally, with most styles, it's very, very easy to do. It's simply using finger catches to open the brackets and then pull the cable out of the system as you can. Actually, what happens in very high value manufacturing sites like automotive, for example, where every minute of downtime is hugely expensive, one alternative you can have in critical processes is to have a spare dress pack. So the whole chain, including the cables and connectors, is held on the side of the cell, a spare one. And that's very, very quick to swap over, because again, it's 3 finger catches, open those, open the brackets up and lift the whole Triflex R system out, including cables. That would literally take seconds to do that, plus however long to undo the connectors. Lift it out, put the new system in and reconnectorize it, so push the connectors back in, and then simply shut the 3 brackets or 4 brackets just by hand. Very, very simple and quick to do, and we have some customers that choose to just send the dress pack back to us, and we investigate what's happened within that, and we can replace parts within that afterwards. So that's another alternative that you can do, but either way it's pretty easy. I would probably rather cheekily add, if the cable fails inside the system, then please consider looking at our ChainFlex robot cables, because we design those to not fail inside your system. So we have a full range of those, so please have a look at those if you have issues with cable failure, because as I mentioned earlier, it's probably to do with the twisting action combined with the flexing, but particularly the twisting, and it will almost certainly be on things like screened cables or large copper core cables where the twisting is really damaging the cores or the screen, and they're just not designed for it. So I'd say if you do have that, again, consider ChainFlex robot cables, CFROBOT cables. Finally, one last question which comes from Dave, and this is a really interesting one, which is, will this system work on a suspended robot? So by a suspended robot, I think what you mean, Dave, is where instead of having a robot on a platform or a plinth on the floor rotating, it's suspended upside down and moves along on a large rail, and the whole robot is essentially upside down and operating that way. There are a few plants where we have fitted systems like this, where by having them on a rail moving along, you have actually more space in the cell for whatever it is that you're working on. Quite common in very, very large scale welding processes, but not so common elsewhere. So can we use this system with that? Yeah, absolutely. The answer is yes. For all of the standard systems that we have without a retraction unit, without a retraction unit, then the system will simply be held in place, and even though gravity is acting the other way, that the systems will work fine. However, if you are using a retraction system, one of the loop retraction systems, one of the round ones, so an RSP, the pneumatic, or RSE, or just RS units, all of those, and in theory, they would start to bow downwards. And all we offer there, very, very simple solution to that, is that the mounting plate has a cover on it. And so when it's upside down, the cover becomes the thing that the retracting Triflex R sits on and moves freely on, but can't move away from it under gravity. So essentially, a cover plate simply captivates that between 2 surfaces and means that it can move smoothly whichever way up it is. And that simply just adds a letter onto a part number when you're ordering C for cover. So yeah, very straightforward and very cost effective. So that answers all of the questions that we have for today. So thank you very much for those. They're really good. And if you have any other questions about this in the future, please don't hesitate to email me or to call me. My details are on the registration page. And thank you very much for your time and attention today.